another episode of Mr. A's Math Podcast. This is going to be a Common Core module review session here. What I'm going to do is go through a series of questions from the end of module assessments. Hopefully this will help prepare you for the upcoming Common Core exam. If you take a look in the comment section, I will post a link to the PDF of the file that I'll be working through. So you can go ahead and pause the video, print that out that you have it with you, or you can just follow along with me. But I do strongly recommend you print out that PDF. So let's take a look at what we have here. In this first question, it's telling us that we have this line where C is the midpoint of AB, and they're asking us to show how to create a line parallel to L, that would be this line here, that passes through B, that point, by only using a rotation about C. So if they just asked us to construct a line parallel to L through B, there's a lot of ways we could do that. Probably my choice would be to construct a parallelogram. You can simply measure that distance from A to there, transfer that up to B, right? So bring it over to that side, and then measure the distance from A to C to B, transfer that over here, and that would create a parallelogram, which would give you a line parallel to L right through B. But there's this extra stipulation here that we have to use a rotation about point C. So let's think about what would have to happen there. If we want to rotate about point C and have this line end up parallel to itself, but through point B, well, what's the degrees that we're going to have to rotate through? If I want this line to be parallel to its image, I'm going to need to rotate through 180 degrees, right? This would be a 180 degree rotation about point C. Now we can actually model that by just taking our paper and spinning it. If I place a pen on point C to act as the center of rotation there, then I can flip my paper, and let's go this way. If I rotate the paper 180 degrees, then you'll see that we have a line that's nice and parallel. And that point there is going to be, when we rotate around, A is going to end up exactly where B is. Now, how do I know that? Well, a rotation of 180 degrees is equivalent to a point reflection through that point. So reflecting A through C would bring it right to B, which means rotating A 180 degrees is also going to bring A right around to B. So all we need to do in order to do this is a rotation of 180 degrees. That's going to give us this line that'll go right through B and be parallel to L. So this says to show how to create. So what we can do is perhaps construct that. And the best way to construct this rotation, since it's 180 degrees, is by just a point reflection. So let's define 2 points on this line. Let's call this point D, and let's call this point E. Alright, so I'm just placing those on the endpoints of that line segment for clarity. It doesn't matter, you could place them anywhere. But once I place those points, to do a line reflection, what I'm going to do, to do a point reflection, is I'm going to take this point here, and I'm going to put it through point C. So it's going to be somewhere on this line. The question is where? Well, since we're rotating 180 degrees, which is equivalent to a point reflection, that distance has to be the same on that side of C as on that side of C. So there would be my point D prime right over there. And we're going to do exactly the same thing for point E. Right? So point E has to go from E through C and end up on the other side here. So E would go through C, and E prime is going to live on that line, and again the distance between E and C is going to have to be equivalent to the distance from C to E prime. And so that would be my E prime over here, this would be my D prime over here, and fortunately I shouldn't have drawn that red line in earlier, but you can see that that does in fact match up quite well, so I eyeballed that okay. If we go ahead and connect these 2 points, right, so my D prime over here and my E prime over here, then we'll get a nice line parallel to the original through point B, and that line has been constructed by a rotation of 180 degrees, which is equivalent to a reflection through a point. That's really handy to remember, that a rotation 180 is equivalent to a reflection through the point, as long as that point is the center of rotation. Normally in the coordinate plane, that would be the origin. In this case, it's point C. Okay, let's take a look at that second question now. Suppose that 4 lines in a given plane, L1, L2, M1, and M2 are given, with the conditions that, now here's where we have to read carefully, L1 is parallel to L2. Now, personally, I would stop right there. If L1 has to be parallel to L2, then I can draw L1 and L2 right now. So I'm just going to draw 2 lines that are parallel to each other. That's the only requirement on L1 and L2. I'll go ahead and label them L1, L2. So I've satisfied that part of the question. Now let's move on in red. M1 has to be parallel to M2, and L1 is neither parallel nor perpendicular to M1. So this part here, L1, neither parallel nor perpendicular to M1, tells me that whatever I do with M1, it cannot be parallel to L1, and it cannot be perpendicular to L1. So any other line will do just fine. So how about this line? That would be a perfectly good M1 line. Certainly not the only choice. Any line that isn't perpendicular or parallel to L1 would work. And then if that's my M1, M2 needs to be parallel to it. So any line parallel to M1 will work fine for M2. Perhaps a line like that. So there's one example of what your picture could look like. The second part says, in any diagram that illustrates these conditions, how many distinct angles are formed? Notice they want us to only count angles less than 180 degrees, and only count two angles as the same if they literally are the same angle. So among these angles, how many different angles are formed? Well, let's go ahead and just number the angles that we have. At this vertex here, we have 1, 2, 3, 4 different angles, which are all acute angles, right? Or excuse me, well, or all less than 180. They come in pairs of acute and obtuse angles, right? This is acute, obtuse, and acute, obtuse. And then at the other intersections, we'll have exactly the same thing. We can call this angle 5, 6, 7, 8, perhaps 9, 10, 11, 12, and finally 13, 14, 15, 16. Now you may recognize this picture. This is a pair of parallel lines cut by not one, but two transversals. And as you can see, we end up with 16 different angles. Why? Well, because there are 4 at each intersection. Right? Anytime two lines intersect, you get 1, 2, 3, 4 pairs of angles. So that's going to explain 16, since we have two lines intersecting with two other lines. That's 4 intersections, 4 angles per intersection. We have 16 angles. Now in this next question, we're being asked to use a straight edge and compass to construct the line of reflection and list the steps of the construction. So the thing you need to remember about a line of reflection is that when you have an image and a pre-image, the line of reflection is the perpendicular bisector. Right? So this is the perpendicular bisector of the image and the pre-image. That means that all we need to do in order to construct the line of reflection is to simply construct a perpendicular bisector. Easiest way to do it is to pick 2 points of the picture that you know are an image and a pre-image pair. So like A and A prime would be a great choice. That's the image, that's the pre-image. You could also use B prime and B, pre-image, or C prime, image, and C, pre-image. I like A and B because they're pretty close to each other, so I'll go ahead and use these. Remember, a perpendicular bisector, you're just going to open your compass up more than halfway, and then you're going to put an arc, top to bottom, go to the other side, and without changing the length that your compass is open, put another arc, top to bottom. Now those two intersections have to be the same distance from A and A prime on both sides, which means they define our perpendicular bisector. So if we just go ahead and connect those 2 points now in space, this is going to be our line of reflection. And you can see visually that the other points line up nicely, right? B and B prime are equidistant and perpendicular. C and C prime also equidistant and perpendicular. So that's our line of reflection. Well, list the steps of construction. So we simply constructed a perpendicular bisector of segment A prime. And I think that would be sufficient. So in this figure we have line segment AB and line segment CD, and L, this guy here, is the perpendicular bisector of both of them. So that tells me that these segments are congruent and that these segments are also congruent. Right? Perpendicular bisector. What does it also tell me? If L is the perpendicular bisector of AB, then that means that A and B are images of each other after a reflection over the line L, just like we were talking about here. Same thing with C and D. C and D are images of each other after reflection over this line L. So, how could we show that AC is congruent to BD using rigid motion? Well, it's pretty simple, really. If you think about AC, we can go ahead and draw it in, right? So, if I reflect, right? If I reflect point A and point C, over line L, they end up at point B and point D, respectively. Right? Respectively means in the same order, so I'm saying that A goes to B and C maps to D. Well, line reflections preserve distance. So if line reflections preserve distance, and A maps to B and C maps to D, then by definition, that means that AC is going to be congruent to BD. Right? Therefore, AC congruent to BD. Show angle ACD is congruent to angle BCD. Okay, well, angle ACD would be this angle over here. Right, we'll call it angle 1. And BDC would be this angle over here. We can call that angle 2. Well, there's a couple of ways we could argue that those are congruent. I see an isosceles trapezoid here, so that might be a nice way to argue that those are congruent. But I think what they're looking for is the fact that a line reflection does not affect angle measure. So if a line reflection does not affect angle measure, then that means that any of the angles in the picture before the reflection will be in the picture after the reflection and congruent to their images. So clearly angle 1, the image of that is angle 2 after that line reflection, so we're okay there. Show AB is parallel to CD. Move this up a little bit for you here. Well, line AB and line CD are both perpendicular to line L, right? And if two lines are perpendicular to the same line, then they are parallel. If you give that a little bit of thought, it should make total sense to you. If I have one line, say my pen, and then I have two other lines that are both perpendicular to it, then there's really no way for me to set this up other than these two lines being parallel. Right? No matter where I orient that pen, if I've got two perpendicular lines, they have to be parallel to each other as long as they're perpendicular to the same line. Alright, now this one's a little bit challenging. We have a picture of a triangle, and they give us several clues about this triangle, so we're really going to have to pay attention to the different information here. So let's see. First of all, it says that CD, alright, so CD, that's this segment here, bisects angle ACB. ACB. So that tells me that this little angle right there and this little angle right there are congruent angles. Now what else do they tell me? So let me just color code this a little bit here. The next thing they say is that AB is equal to BC. Now that's equivalent to tell me that the segment AB is congruent to the segment BC. So what will that tell me about the picture? Well, if AB is congruent to BC, then if you ignore everything else except ABC, can you see that that's now an isosceles triangle? This side AB is congruent to this side BC, which means that that large angle there and this large angle here have to be congruent. If you can't see that, I'll draw it separately for you, and this is a good thing to do in general. If you're ever unsure about what's going on in a picture, draw it separately. Here's triangle ABC. They just told me that those two segments are congruent. So in blue, what I'm marking is that this angle, A, right, or BAC, is congruent to this angle, C, or BCA. BCA is this large blue angle, okay? And let's see, what else do we know? Angle BEC is 90, well, okay, then we can see that in the picture. And DCE is 42, again, we can see that in the picture. So, at first this might seem kind of tricky. There's not an obvious equation to set up, and that's what we need to do here if we're trying to find the measure of angle A. But let's try to proceed and see what happens. I'm looking for the measure of angle A, so let me go ahead and call that X. All right, that's the angle I want. Well, if angle A is X, then we know that angle C is also X, right? That large angle up there. But hold on a second. Angle C is this entire angle, and there's two pieces that are the same. So if the whole angle is X, then these would each be 1/2 X. That's a little bit inconvenient. So I'm going to change my mind about this X. I'm going to say, you know what? Let that be 2X. All right, so the angle I'm looking for is 2X. That means these are both 2X. And what does that do for me? Well, if that's 2X, then this other angle is also 2X, and each of these little red guys is X. Does that make sense? Now, it would be perfectly okay to have left that X and make these 1/2 X and 1/2 X, but quite frankly, I would just assume have an X, then a 1/2 X. So this is a personal choice. Well, can you see how we can solve this problem now? we're actually in pretty good shape, I think. Let me redraw the large picture. We've got a 2x angle there. That's a 90-degree angle right there. And how big is this angle up here? Well, that's 42, and that extra little piece is x. So this would be 42 plus x. Does that make sense? Well, now we've got one triangle. We have an expression for all three angles we can solve. Normally the angles in a triangle, well, would add up to 180 degrees. Since I've already got a 90-degree angle, then these two angles should be complementary. In other words, 2x plus 42 plus x should equal 90 degrees. Well, that's a pretty simple equation to solve. We've got 3x altogether on the left-hand side. If I go ahead and subtract 42 from both sides, I'll end up with 48. 3x equal to 48. Divide by 3, and I get x equal to 16. Now here's the thing you got to be a little bit careful about. I'm tempted to put a box around that because this is an answer. But is it the answer I want? Remember what they're looking for, the measure of angle A. Well, angle A is actually 2x, isn't it? So the measure of angle A is going to be not 16, but 32. Now let's talk test strategy for a minute. I've got an answer. I worked very carefully. I feel pretty good about what I did. But what could I do to make sure that that answer works? Well, I could go back and plug it in. If angle A is 32, right? Well, if x is 16, either way. So then this big triangle here, let's take a look at ADC, right? That's a triangle. Well, let's stick to one that we know and fill in the angles here. So that's a right angle there. And in the large triangle, ACE, okay? If I sub in x for 16, then 2x is going to be 32. So that would be that angle A down there, right? Now we're supposed to have 16 for each of these x's. Okay, well if that's true, then here's what we have. 16, 16. Now these two have to be 42. So if x is 16, what's this other angle going to be to add up to 42? Think about that for a second. Count up from 16. You can add 4 to get to 20. 20 more will get you to 40. Right? So that's 24 plus another 2. That would be a 26-degree angle. Well, let's stop there for a second. Does that work? Is that 180? 16 plus 16 plus 26. That's 32 plus 26. That's 58 plus 32. Is that 90? Yes, it is. So that's looking pretty good. So this is an opportunity to just check my work so I can feel pretty confident about the answer before. Alright, so in this question, we're given a picture and told that AD is the angle bisector of BAC. Alright, so if I go to my picture, if AD is the angle bisector of BAC, well then that means that those two angles there are congruent, and they've already marked those for me, so I won't go ahead and mark them again. They also tell me that we have some straight lines, that we can tell from the picture, so it's not really information. And AD is parallel to BC, which they've also gone ahead and marked. I'll just mark that a little bit clearer because those angles are a little bit small for me, those arrows. So they want us to prove that AP is equal to AC, which is equivalent to proving that AP is congruent to AC. Right? I like to think in terms of congruence. Helps me organize my thoughts. So the first question I'd like to ask myself is what would have to be true, right? What would have to be true if AP was congruent to AC? Well, if AP is congruent to AC, then doesn't that mean that this angle over here, which I'll call angle 1, and this angle over here, which I'll call angle 2, would have to be congruent, right? Because you can see triangle APC would have to be isosceles if that's the case. So those angles would have to be congruent. So here's the next thing I start to wonder. I'd like to get those angles congruent to each other. Are there any angles that I know that they are congruent to? Well, focusing in red for a minute on angle 1, hopefully you would agree with me that angle 1 is in fact congruent to that little angle right there. How do I know that? Well, we have a set of parallel lines there, and those are alternate interior angles. So angle 1 and angle, let's say, 3, those are congruent angles. I'm going to do the same thing with angle 2. Angle 2, I have some parallel lines here. Well, hold on a second. Isn't angle 2 corresponding to this angle down here? So that means that this angle is going to be congruent to 2. Whoops, I labeled it 2. That's no good, so let's call that angle 4. So angle 2 and angle 4 in blue are going to be congruent. Likewise, angle 1 and angle 3 in red are going to be congruent. But wait a second, don't we already know that angle 3 is congruent to angle 4? That was given to us. So that's going to allow us to do a substitution. what would this proof actually look like? Well, you could write it out 2 columns, or you could use a paragraph form for the regents. So let's go with a paragraph form. Might be a little bit easier in this case. So let's start with the fact that AD is parallel to PC. So if AD is parallel to PC, therefore, right, we can say that angle 1 and angle 3 are congruent. And we can also say that angle 2 and angle 4 are congruent. Now, why is that? Well, that's because parallel lines cut by a transversal form congruent alternate interior and congruent corresponding angles. So now we have 1 congruent to 3 and 2 congruent to 4. Now hold on, they also told us that AD is the angle bisector of BAC. So if AD bisects angle BAC, therefore, right, this little symbol means therefore, if you're not familiar with that, angle 3 is congruent to angle 4 because an angle bisector divides an angle into 2 congruent angles. So if 1 is congruent to 3 and 2 is congruent to 4, well, if 3 and 4 are congruent, this is our connection right here. All right, so look what we can do. Now we can say angle 3 is congruent to 1, so angle 1 is congruent to, instead of 4, we can put 2, angle 2, and this is by substitution. Well, if 1 is congruent to 2, now this is an isosceles triangle. And we can claim what they asked us to show, which is that AP is equal to AC, or more precisely, AP congruent to AC, because in a triangle, angles opposite congruent sides are congruent. And therefore, AP equals AC. And that is what they had asked us to show. So this is an example of just another way to write a proof. You don't have to necessarily do statement reason. This is sort of a paragraph form, just a little bit looser. All that matters in a proof is that you have clear statements and clear reasons. All right, so notice, even though I don't have statement reason, I'm still making statements, and I'm giving reasons for those statements. Making statements, giving reasons, making statements, giving reasons. That's all you need for a proof. So number 7 is a very quick one. They're giving us this pair of triangles, and we can see clearly right angles in the picture. They tell us that AB is congruent to DE, so I'll go ahead and mark those. And they tell us that AC is congruent to DF, so I'll go ahead and mark those. And then angle A is congruent to angle D. So let's see, angle A is up there, congruent to angle D down there. So what criterion for triangle congruence implies that those triangles are congruent? Well, we've in fact got a couple of choices here, right? So with the information they've given us, let's see. We could say side, angle, side, right? We have in red this pair of sides, this pair of angles, this pair of sides in that order. So we could use side, angle, side, triangle congruence. However, with the right angles in the mix, we could also use angle, side, angle, right? An angle, then a side, then an angle in that order. So that'll work just fine as well. ASA, or angle, side, angle, triangle congruence. There's another one that's a little bit sneaky. A lot of times students forget about this one. If those are right angles, then what kind of triangles are these? That's right. And if we have a congruent hypotenuse and a leg inside of a right triangle, then we can also use the old hyp-leg triangle congruence. A lot of times people abbreviate this HL for short. I'll just write hyp-leg, or in parentheses HL, triangle congruence. So any one of those three would work given the information they told us. We actually know quite a bit about this picture. Describe a series of rigid transformations that shows the triangles are in fact congruent. So there's a lot of ways you could go here. Let's talk about one possible set of rigid transformations. So one thing you could do is start by translating this triangle along the vector CF. So if you translate, right, triangle ABC along vector CF, that's going to map point C onto point F. And your picture at that point would look something like this. You'd have the triangle FED, right? And then you'd have the other triangle sort of off in this direction, ABC. Well, now I've got one of the vertices matched up, but not all three yet. So a second thing I could do, in terms of rigid motions, is now I want to close this gap. I want to bring point B onto point E. So I could now rotate triangle ABC about point C or F. Remember, you need to have a center of your rotation, mapping B to E. And it's also a good idea with a rotation to give an angle. So we can rotate through an angle equal to the measure of angle BCE. Right, so angle BCE is this angle right in here, and that's the angle we need to rotate through to bring B right to E. And if you think about what the picture looks like after that, well, you'd still have the original EFD triangle right here, right? But now the other triangle is sort of sitting right on top of it. CF, this is point BE, and A's over there. So can you see how to finish this? All we need to do is a line reflection over that line right there. So you could reflect triangle ABC over line CB, mapping A onto B. Oh, excuse me, A onto D. And that is one example of a series of rigid motions that would map the first triangle onto the second. There's lots of other things that you could have done. You could, for example, bring the first triangle all the way over to point D, so you could bring point A right down to D, and then it would kind of go that way. You could rotate D it around until the E matches up there with the B, right? And then you could do a reflection. But it's going to be a combination of a translation, a rotation, and a reflection in some order. Generally speaking, I like to translate first, then rotate, and then reflect. Alright, so that'll be part A and B there. Okay, so for this next one we have a construction, and they're asking us to construct a square with side AB. So this has to be one of the sides of our square. Alright, well that actually makes it a little bit of a harder construction than if I just had to construct a square giving that line segment. So let's think about what a square needs. We're going to need a right angle there, and we're going to need a right angle there. So what I'm going to start by doing is extending line AB. I'm just going to extend it right out past A. And so since they asked me to list the steps of the construction, I might as well keep in track of what I'm doing. So extend AB through A. Okay. And now what I'm going to do is create a point on the other side of A that's equal distance from AB. Right? So you see that there? I'm going to go ahead and create a point right over there. And I'm actually going to do like a full quarter circle here because I know what's going to happen in the future. Remember, we're trying to make a square. So one side of my square should end up right over here somewhere, right? I just don't know exactly where yet. So I'm going to go ahead and leave that mark there because that's the right length. It's the length of AB, and I just don't know where yet. So now I've got this intersection there. Let's go ahead and call that B prime since it sort of came from B. All right? So we'll write that down as well. So construct B prime on line AB such that ST means, you know, following this particular condition, such that AB prime equals AB. All right, so that's equidistant from that. And now I'm in a good position to create my perpendicular bisector, right? Because if I do a perpendicular bisector of B and B prime, that's going to give me a line perpendicular to AB right through point A. So with my compass on B and open more than halfway, I'm going to do an arc top to bottom, and then I'll take that same distance, bring it over to B prime, and place an arc top to bottom. Now, when I connect those 2 points, a couple of things are going to happen here. First of all, I now have a line perpendicular to AB that's going to go right through vertex A. Okay? And I'll bring it all the way to this intersection, even though the only part I really need is over here. Right? But wait a second. Where that line intersects with that circle, that's also the right length for the square, isn't it? So in fact, I can go ahead and make this solid right here, because that's going to be point, let's see, A, B, C, that will be D, right up there. Does that make sense? Right? That distance and that distance are the same. So what did we just do there? Step 3, construct perpendicular bisector of B, B prime Step 4, label point D on the perpendicular bisector such that AD equals AB. Right? So I choose point D so that AD to AB is the same distance. So now I've got one right angle and I've got two sides that are congruent. And I'm pretty close to done actually, because all I need to do now is take my side length here, and I know that the next corner has to be somewhere right up in there. So if I do an arc from A out there, right, so that's the right length, I just need to know where on that arc it is. Well, if I take that very same length from point D, right, and I make an arc, now that's how long that side has to be. And where those two intersect right there is going to be my point C. So there's point C, and we can now complete the square. Grab my blue pen again. So I'll go ahead and connect these vertices. There's square ABCD. Okay. And what was the last thing we did? 5, construct point C equidistant from B and D such that DC equals CB equals AB equals AD. So all four of my sides are congruent. And now I've got a square. Perpendicular bisector gives me the right angle, and by marking off those distances, I know that I have a perfect square. Okay, so this page has a pretty quick one here. So we have a square and we're performing some rigid motions on it. It says the first one is a reflection through line BD. It says that right here. Second rigid motion is a clockwise rotation, 90 degrees, and then we're going to bring it back to the original position. So let's talk about what these three rigid motions do. Well, ABCD, if I reflect over the line BD, let's go ahead and draw that in. So the line BD is the line connecting, of course, vertices B and D. So that's the line right there. So what do you notice right away? What won't change when we reflect over the line BD? Point B and point D, right? So those are going to stay exactly the same. B is up in that corner, D is down in that corner. Now what will change? Well, that would be A and C. And they're going to flip-flop, right? A is going to end up where C is going to end up where A is. So we have point C up here, point A down there. Alright, so there's our reflection through line BD. A and C change, B and D remain the same. By the way, there's a nice word for that. It's called invariant. So point B and D are invariant under this reflection. Invariant means does not change. Right? In as in not, variant like vary, they do not change. The second rigid motion we need to do is a 90-degree clockwise rotation about the center of the square. So hold on a second. If I'm rotating about the center of the square, well, that's somewhere around there, correct? Are any of the points going to be invariant under a rotation around the center of the square? No, everything is moving here, right? Now you have to pay attention to direction. 90 degrees clockwise, think about the hands of a clock. 12's up there, 3, 6, 9, right? So this is clockwise in that direction. So what's going to happen? Well, point B used to be in the upper right-hand corner. Now it's going to end up down in the lower right-hand corner. Point A used to be in the lower right-hand corner. Now it's going to end up in the lower left-hand corner. Right? Point C will end up where point B is, and point D will end up where point C is. So there's our square after a 90 degrees clockwise rotation about the center. Now the third one we have to figure out for ourselves. It says, hey, what's the rigid motion that's going to take this ABCD square and map it back onto this ABCD square? So the first thing I'm going to look for is, are there any invariant points? And before I do that, I notice I have two B's here. So let me just go back, something went wrong. Oh, it looks like I didn't move my point C. Right, so A went to there, good. D should have gone to there. So this is actually a point D up in this corner. That's pretty important. I'm glad I spotted that. Okay, so I've got D there. C ends up over here. So that should be my C right there. Okay, and B. So let me just double check that. A, D, yep, C, B. Okay, so hopefully maybe you caught that on your own. I just found it now. So how am I going to turn ABCD into ABCD? The first thing I'm going to look for is, are there any invariant points? So like A, no. D, no. B, no. B, no. Okay, so everything's going to move. Well, how does it move? B looks like it has to go up this way. It's got to end up right up there. But C has to end up down there. Oh, so B and C are flip-flopping, aren't they? That makes me think about a line reflection. I wonder if that'll work on the other side of the square. Over here, A used to be in the bottom left. Now it's in the top left. And D used to be in the top left. Now it's in the bottom left. So are D and A flip-flopping as well? Yes, they are. So what's happening here is this is going to be a line reflection over this line. Right? This line of symmetry, like that. If we reflect over that line, then we'll end up with B and C flip-flopping and A and D flip-flopping. So what's our final description? Well, this would be a reflection over, and there's a couple of ways you describe it. Probably the easiest way would be to say the perpendicular bisector of BC or the perpendicular bisector of AD. So reflection over the perpendicular bisector of BC or AD. Another way you could describe it was to say to find the midpoint of BC and the midpoint of AD and connect those with a line. And that would also be the same as the perpendicular bisector. Okay, so for number 9 we have a little bit of a proof in front of us here. And we have a parallelogram, ABCD, that's the larger one, right? So that tells me that those sides are parallel, congruent, all kinds of stuff there. Also, M and N are the midpoints of AB and CD respectively. All right, so that's worth mentioning. So if M is the midpoint of AB, then that means that those two segments are congruent. If N is the midpoint of DC, that means that those two segments are congruent. Now, I'm going to go ahead and extrapolate a little bit here. Since this is a parallelogram, DC is congruent to AB, right? Opposite sides of a parallelogram are congruent. Well, that means that if the whole pieces were congruent and we cut them in half with the midpoint, aren't the halves also going to be congruent? So I'm actually going to go ahead and mark that with a second tick mark there, but I am going to need to say something about why that's the case. I've actually got all 4 of these congruent here. Let's see, what else do we know? Nothing. Prove that AMCN is a parallelogram. So the goal here is to get AMCN, this smaller parallelogram, to be a parallelogram. Well, there's a lot of ways to prove a parallelogram. My favorite, and probably the easiest more often than not, is to find one pair of opposite sides that is congruent and parallel. Looks like I'm going to be able to get that here. I've already got them, at least I have the beginnings of an argument that they're congruent. To get them parallel shouldn't be too hard because I know that the large pieces, right, AB is parallel to DC, so surely that part of the line is going to have to be parallel as well. So let's go ahead and sketch this proof out. As with the last one, I'm going to use more of a free-form style of proof rather than a statement reason. It's just a little bit easier to work with on this page, and it gives you a little more freedom when you get to the regions. So I'm going to start by saying ABCD, the original shape, is a parallelogram. Okay? I like to use the little picture of a parallelogram in my proofs. Since you don't know who's grading this, you might want to start by saying, hey, look, when I draw that picture, I mean parallelogram. This way there's no confusion. So if ABCD is a parallelogram, therefore, that's what that double arrow means, side DC is parallel to side AB. Also, I may want to mention that side DC is congruent to side AB. Right, those are both going to be important for my argument here. So let's go ahead and color code a little bit. If DC is parallel to AB, then what can I say about this picture? Well, NC is going to be parallel to AM. Right? So this part NC of DC is going to be parallel to AM, this part of AB. Now why is that? Well, that's because if two lines are parallel, oops, I didn't spell 2 right. If two lines are parallel, then any part of those lines, any parts I should say, of those lines are parallel. Right? In other words, if I have two lines that are parallel, then a part of that line is going to be parallel to a part of the other line. You don't have to have that exact reason. If I wrote it again, I probably wouldn't write it the same exact way, but convey the idea that you're understanding that since these lines are parallel, their pieces also have to be parallel. Alright, now what about this thing about DC being congruent to AB? Well, since we know that N and M are midpoints, right? So N midpoint DC and M midpoint of AB, right? So what's that tell me? Well, if those are midpoints, then therefore, certainly DN is congruent to NC, and AM is congruent to MB, right? Because a midpoint divides a segment into two congruent segments. But that's not exactly what I need to say. What I'm really trying to say is that NC is congruent to AM. Yeah? So maybe I could finish that by saying AM congruent to NC, because if two segments are congruent, then half of one segment is congruent to half the other. Right? So again, I'm explaining my reasoning. Statement, reason. I know that DC is congruent to AB, so if AM is congruent to, AM has to be congruent to NC, because if these two segments are congruent, then half of one of them, AM, must be congruent to half the other, NC. And so look what we have here now. We've got NC parallel to AM. We have NC congruent to AM. So I can now go ahead and say AMCN is a parallelogram because a quadrilateral, let's make a nice good reason here, with one pair of opposite sides, both congruent and parallel, right? A quadrilateral with one pair of opposite sides, congruent and parallel, is a parallelogram. And I like to finish my proofs with a proof box. You know that if you're in my class. If you're not familiar with that, that's a way to finish a proof. It sort of says, like, there you go, like that's what you asked me to prove. So this would be a nice way to prove this, fairly straightforward. If you wanted to do it in a statement of reason form, that's certainly quite fine. I just want to show you that there's some options. You don't need to be so rigid on the regions. You just need to get the idea across of what you're trying to say. Okay, so in this picture we are looking at a right triangle, that's the large triangle I'm referring to, with a line that's perpendicular to the hypotenuse. Now you should know that a line perpendicular from a vertex that's perpendicular to the opposite side is an altitude. So this is a right triangle with an altitude to the hypotenuse. And that's really important. Anytime you see that, you should be thinking, aha, I am going to have mean proportionals in this picture, right? Mean proportionals in a right triangle. These triangles are all similar to each other. Now, that's something you should know. It's actually asking you about it in this first part of the question. What is the relationship between the large triangle and the two smaller ones, and why? So let's go ahead and sketch that out quickly. In this triangle, if I redraw just the large triangle in the center, and then I'll draw the smaller triangle on the left and the smaller triangle on the right. Okay? So let's label what I know. Well, these are right angles here. These are also right angles. And let's see, if I color coordinate a little bit, would you agree with me that that angle and that angle are congruent? They are literally the same angle from the original picture, right? This is the angle right in here that we're talking about. And if I grab my blue pen, hopefully you would also agree that that angle is congruent to that angle right there, because they are, again, literally that blue angle from right there. One final thing you might want to notice is that in this middle triangle, the red and the blue angles are both present, right? So we've got a 90 degree, a red, and a blue. Well, that means that the red and the blue are complementary, aren't they? So in this triangle, where I have a 90 degree angle and a red, what's that missing angle have to be? That's right, it's got to be a blue angle. So if that's a blue angle, we can make the same argument over here. We've got a 90 degree and a blue angle. So with a 90 and a blue, what does the third angle have to be here? Once again, red. So you see that we have three triangles here which are all similar to each other, right? By angle, 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 in fact, similarity. And over here, angle, angle, angle. So the answer to the first part of the question is they are all similar triangles by angle, 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 triangle similarity. You can also write angle, angle, angle as simply angle, angle, triangle similarity. Since the angles in a triangle add up to 180, having any two angles is good enough. The third one just has to happen. Now it says solve for h, x, and y. So there are a couple of proportions that you should know about this picture. So I'm going to sketch them out for you quick. Let me redraw that first triangle so I can label the pieces. So if I call this the altitude, because it is, and then I can call this leg A and leg B. I'll call this P leg A, which stands for the projection of leg A, and I'll call this P leg B, which stands for the projection of leg B. So if you imagine the sun up here, that's where the shadow would be for those two. And then I can go ahead and call this the hypotenuse. Okay. So in this picture, we need to know two proportions. Let me start with the altitude. So the altitude is the mean proportional. That means it would go in the mean positions in the proportion, bottom left, top right, between the two projections of the legs, right? So P leg A and P leg B. Depending on who your teacher is, they might have taught you these as, segments, segment 1, segment 2, or pieces or something. They are formally projections, but it doesn't really matter what you call them as long as you understand this relationship. Now, where does this come from? It comes from these two similar triangles here. If you work out the proportion with this triangle and this triangle, you'll find that this is what you get. The other relationship that we want to know focuses on the legs. So the leg, let me just move over here a little bit, is also a mean proportional. I'll write leg A. The leg is the mean proportional between the hypotenuse of the whole triangle and its projection. So if I'm working with leg A, that would be P leg A. It's also true for leg B. You just make all of these B's, right? So you can also say hypotenuse over leg B equals leg B over P leg B. Now these three proportions are what we're going to use to solve for h, x, and y. Let me just bring that original picture back down here, and I'll put it side by side with this one. So in the original, we had h being there, x, y. This was 30, 16, and this was 30. So as you can see over here, we're going to have too many variables. We've got an x, an h, a y. We don't know what any of those are, so we'll instead turn to these other two proportions, using leg A and leg B. See, leg A, I know what that is, and leg B, I know what that is. So starting with leg A, we could write, let's see, hypotenuse over leg A, that would be 34 over 16, equals leg A, 16 over P leg A, 16 over x. That means that 34x equals 16 squared, and x is equal to 16 squared. And when I plug that into my calculator, I get h is about 14.117. Now just a word about test taking and giving yourself the best shot for all the points. Don't leave your work scattered all like that. They asked us to solve for h, x, and y. So let's go ahead and tell them that h is about 14.117, that x is about 7.529, and that y is about 26.470. And I'll put a box around that so it's really easy for the grader to find my answer. So a lot going on this page. You want to make sure that you know these proportions. When you have an altitude to the hypotenuse of a right triangle, then you've got these three proportions, which are really just two proportions. One comes in two varieties there, and you can use those really nicely to solve problems. Of course, the fallback position, if you don't know those proportions, is to simply use the similar triangles and set up a proportion with the ratio of corresponding sides. Okay. In problem 11 here, we have a triangle ABC on the coordinate plane, and it says that we're going to dilate this triangle by a scale factor of 2, and that's centered at the origin. Okay, so first of all it says identify the coordinates of the dilated triangle ABC. So let me go ahead and do that in blue. So remember what a dilation does. It pushes points further away from the origin. So A started off at 3, 2. If A was at 3, 2 to begin with, then it's going to get dilated by a factor of 2 to 6, 4. Right? Both of these numbers are going to double. So A is going to end up at 6, 4. There's our A prime, and we're going to label it 6, 4. What about B? Well, B is at 0, -1. So let's see, B is at 0, -1. So multiplying by 2, that's still going to be 0, but it's going to be negative 2 now. So B prime will be down here at 0, comma, negative 2. And C used to be at negative 3, comma 1. So that was negative 3, comma 1. When we dilate by 2, we'll end up at negative 6, comma 2. So negative 6 over there, comma 2. That'll put us right there, C prime, negative 6, comma 2. All right, if I get my little straight edge here, I can connect those dots to give us a picture of the triangle. Now, the triangle, when we dilate by a scale factor of 2, all the sides should be twice as long. However, and this is going to become important later in the question, you may notice that this new triangle looks more than twice as big as the original. And that's because the area has actually been multiplied by 4. When you dilate by 2, you're changing both lengths, the base and the height of this triangle, by a factor of 2. So if you think about if the area of a triangle is base times height, and then you dilate that triangle to like a new triangle, where the area of the new one, let's call that A prime, well, area is base times height over 2 for a triangle, that's important. So if the new area is 2 times the original base, times 2 times the original height, still divided by 2, well, look at what you get there. A prime is equal to 2 base height over 2 times 2, right? 2 times 2, base height over 2. Well, wait a minute, that's 4 times base height over 2. That's 4 times the original size, right? The original triangle was base times height over 2. Now it is 4 times as large. So that's going to be important here. So part A we've actually satisfied. The new coordinates are 6, 4, 0, negative 2, and negative 6, 2. Part B says, is the first triangle similar to the second triangle? And if so, explain. Well, yes. This is easy to explain because dilations do not affect angle measure. So all corresponding angles are congruent and the triangles are similar by angle, angle, triangle similarity. That'll be a nice full explanation for that second part. Finally, they want to know what is the area of triangle ABC and triangle A prime, B prime, C prime. So to find the area, there's a couple of things that you could do. You could either split this triangle up into workable shapes or box it out. I'm going to show you boxing it out because it's a method that we've done in class, at least if you're in my class, and it works on any kind of irregular shape. Now this triangle we could actually break up into 2 triangles we could deal with, but it might be a little bit easier to think about boxing it. So if I box this out, hopefully you can see this. I've got a 3 by 3 triangle right there, right? 3 by 3. So that's 9. Let's go ahead and call that triangle 1. I've got a, let's see, this is a 1, 2, 3, 4, 5, 6 by 1 triangle there, and I'll call that triangle 2. And then I've got a 1, 2 by 1, 2, 3 triangle there. That's a 2 by 3. I'll go ahead and call that triangle 3. And this is all inside of a rectangle that is 6 by 3. So the area of triangle ABC, right? The area of triangle ABC is equal to the rectangle minus triangle 1 minus triangle 2 minus triangle 3. Right? I'm just doing the area of the rectangle, and I'm going to take out these 3 triangles that I don't want. Alright, so the rectangle is 6 by 3, that's 18, minus triangle 1 is 3 times 3, which is 9, divided by 2. That's 4.5. Minus triangle 2 is 6 times 1, that's 6, but divided by 2 is 3. Minus area of triangle 3, that's 2 by 3, 6, again divided by 2, that will get us back to 3. Alright, so remember, area of a triangle is 1/2 base times height, that's why I keep dividing by 2. So we have 18 minus 4.5 minus 3 minus 3, well that's 6, 10.5, so this is really 18 minus 10.5, right, which is 7.5. So the answer to this question, what's the area of triangle ABC? The area of triangle ABC is equal to 7.5 units squared. Right? Remember, area is square units. Now, the area answer to the second question, what's the area of triangle A prime, B prime, C prime? So there's 2 ways to do that. you certainly could go ahead and box out this larger triangle and do the exact same thing we just did. Find the areas of those three triangles you don't want and take them out of the entire rectangle. But I also happen to know that the area of triangle A prime, B prime, C prime is going to be equal to 4 times the area of triangle ABC. That's because of what we talked about up here, that when you multiply by a scale factor of 2, when you dilate by 2, the area goes up by a factor of 4, the square of the dilation. So 4 times that, well, that would just be 4 times 7.5, and that's just 30 units squared. So that's going to be the area of A prime, B prime, C prime, and that'll be the area of triangle ABC. A lot going on that page. Make sure you go back through this and make sure you understand all of these pieces. Okay, so in number 12 here, we have a figure where it says if you rotate EAB about E by 180 degrees, so EAB is going to be rotated around point E, that means E won't change, and AB is going to end up down here at A prime, B prime. And we're told that these are parallel, A prime, B prime, and CD. We want to prove that EAB, that's the original triangle, is similar to EDC, that's this larger secondary triangle. Well, the first thing I'd like to note is that triangle EAB is congruent to triangle EA prime, B prime. How do I know this? Well, the only thing we did to get from this triangle to this one is rotate. And rotations are isometries. Okay, so how do I know that triangle EAB is congruent to triangle EA prime, B prime? Well, rotations are isometries. Or, in the Common Core parlance, they are what is known as congruence transformations. That means that they don't affect the congruence of objects. The image and the preimage are congruent. So if I can prove that this triangle, EB prime A, or EA prime B, either way, is similar to EDC, then I'll basically be done, because these two are congruent. So if the image is similar to the triangle, then the original is similar to the triangle. Well, that's actually going to be very easy to prove. I'm going to number a couple of angles here to make it easy to see what's going on. So let's go ahead and talk about this angle as angle 1, right up there in the top. Right? And then I'll go ahead and name this angle 2 and angle 3. And I'm going to mark those in red. So before I do, take a look at angles 2 and 3, and what do you notice about those? Those are corresponding angles, aren't they? And since these lines are parallel, those corresponding angles are going to be congruent. That means I've got a pair of congruent angles between those two triangles. So what am I doing with angle 1 up here? Well, doesn't the little triangle EA prime B have angle 1 in it? And doesn't the large triangle EDC have angle 1 in it? That means that angle 1 is congruent, right, to itself, reflexive. So this is going to be a very simple proof. We have A prime, B prime, parallel to CD, and that was given to us, right? So therefore, angle 2 is congruent to angle 3. Why? Well, that's because parallel lines cut by a transversal form congruent corresponding angles. So we've got that pair of angles congruent. Also, angle 1 is congruent to angle 1 by reflexive property. So we have triangle EA prime B prime similar to triangle EDC by angle triangle similarity. Great, because we already know that EAB is congruent to EA prime B prime, right? So we can simply do a substitution here. We can say triangle EAB is congruent to triangle, is not congruent, this is similar, right? So triangle EAB is similar to triangle EDC by substitution. And that is what they asked us to prove. So that's a pretty straightforward proof, taking advantage of the fact that rotations are isometries, that is to say congruence transformations, and a quick angle-angle proof using corresponding angles and one reflexive on the image and the larger triangle down there. Quick substitution gets us the original triangle, similar to that larger triangle. The second half of this page is also a pretty quick one. So question number 13 here, so just straighten this out a little bit, is just asking us to find some sine cosine values inside of this triangle. Just remember what sine and cosine are. Sine is opposite over hypotenuse, right? So if I go the sine of r, that would be opposite from r over hypotenuse, 15 over 17, as opposed to the sine of s, opposite from s is 8 over hypotenuse, 17. And then of course we have the cosine, which is adjacent over hypotenuse. So the cosine of r, the adjacent to r would be 8 over 17. And the cosine of s, now the adjacent side is 15 over 17. Tangent, of course, is opposite over adjacent, or sine over cosine, however you prefer to think about it. So with regard to r, the opposite over adjacent would be 15 over 8. And with regard to s, the opposite over adjacent would be 8 over 15. Now you might notice in this first couple here, the sine of r and the cosine of s are the same number. Also, the cosine of r and the sine of s are the same number. That's not a coincidence. In fact, it's what they're asking us about in the second part of this problem. Why is the sine of an acute angle the same value as the cosine of its complement? Notice that angle r in this first triangle, in the only triangle we have, and angle s are complementary angles. That's because this is a right angle, so these two have to add up to 90, so you get 180. Well, this is the reason, because the sine of r, right, so the sine of one angle, let's say, r's opposite side is the adjacent side to angle s. And the same thing is true for s, right? The opposite side of s is the adjacent side to r. So since the opposite side of one angle is the adjacent side of the other, the sine of one equals the cosine of the other. This is because they are in the same triangle. So that's an important relationship to keep in mind. If you have two angles that are complementary, then the sine of one angle is going to equal the cosine of the other, and vice versa. Alright, so we've been at this for a little while. This is question 14, the very last one, and it looks like we're going to finish out with some trig. So in this picture we have a radio tower, which is represented by just this line DC in the tower, in the picture, right? The rest of the stuff are wires. It's just that tower is just that segment right there. They call these long cables guy wires, these cables that anchor it to the side. And they tell us that point A is 200 meters from the base of the tower. Well, that would be this distance here, right? Point A from the base of the tower, that's AC. So that distance right there is the distance from A to C, which I'm already pretty unhappy with because that's very tiny. So I'm not loving this picture. So the first thing I'm going to do is redraw this picture in a way that makes me happier. So I'm going to sort of exaggerate the angle here. There's A for me. There's going to be my C, and then I can also draw in this other segment with B. So what they just told me is that this distance is 250 meters. They also tell me here that angle BAC, so that would be BAC, is 59 degrees. Okay, so let's see what they're asking us to do. How long is the guy wire round to the nearest tenth? Let's see, is there only one guy wire? I thought there were two. A radio tower is anchored by long cables called guy wires, such as AB in the figure below. Okay, so I guess AB is the one that they're talking about for the guy wire. So when they ask me for how long it is, that's going to be this piece here, AB. Well, this is right triangle trig, right? This tower is going to be perpendicular to the ground. So I've got an angle. The hypotenuse is what I'm looking for. The adjacent side is what I have. So think sine, cosine, tangent. What can I do with an adjacent and a hypotenuse? It's always handy to keep in mind SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So with an adjacent and a hypotenuse, that's going to be cosine. So we can go ahead and say the cosine of 59 degrees equals the adjacent over hypotenuse side, 250 over x. A little bit of algebra, we can cross multiply here. If you like, you can think about putting that cosine 59 over 1. Right, so 1 times 250 equals x times cos 59. And you get x times the cos of 59 equals 250. Finally, you can divide on both sides by cos 59, and you get x is equal to 250 over the cosine of 59. Notice I haven't gone to my calculator yet. This is a very good habit to get into. Always solve for x algebraically before you go to the calculator. Helps eliminate common mistakes, and it also shows the grader clearly that you know what you're doing. At this point, though, I will have to go to the calculator, and I'll type in 250 divided by cos 59. I don't know if you can see that or not. And then we got about 485.4010. Now they asked me to round to the nearest tenth, so that would be that decimal place. So I'm going to tell them that the height is or the length of the wire is approximately 485.4 meters is the units that we are working in. Question B, or part B. How far above the ground is it fastened to the tower? Well, it would be the guy wire that we were talking about here. That's the subject of the previous sentence. So the distance now we're looking for, I guess I'll work in red, is from the ground up to B. All right, so let me call that H because it's sort of like a height. Well, now H is the opposite side from 59, and this would be the adjacent. So with an opposite and adjacent, I'm talking about tangent now. So tangent of 59 equals H over 250. Tan 59 equals H over 250. Now before I finish this, some of you may be thinking, hey, Mr. A, we already know what x is now. Can't I just use Pythagorean theorem to find out h? And the answer is absolutely you can. Although, please be careful and use more than just that 1/10 place if you're going to use Pythagorean theorem, because that's an approximation and there are some other digits after that. So you want to use like the 4010 and maybe even a couple of more to make sure that you don't lose any accuracy. This way I'm using the numbers they gave me, so I know I'm going to be completely accurate. This one's actually a little bit easier to solve too. When I cross multiply, again you can think about tan 59 over 1. You just get 1 times h equals 250 times tan 59. So h is whatever 250 times the tangent of 59 degrees is. So what's that going to be? Let's see. H, I'll make sure I'm in the right mode here. I am, that's a good thing. 250 times the tangent of 59 is going to be approximately 416. It doesn't tell me how to round, so this is actually, I'm getting about 416.0698 or so. Since it doesn't say how to round, I'll round again to the nearest tenth, so we'll say the height is about 416.1 meters off the ground. And then the final question, how tall is the tower? All right, so DC, I never put a D on that picture. DC, if angle DAC is 71. So angle DAC 71. Well, I feel like I've pretty much used this picture up. It's getting a little bit cluttered, so I'm going to go ahead and redraw the picture. So really now I'm only thinking about this triangle, DAC. Right? I know that this distance is 250 from the original part of the question, and now they're asking me to find this distance. So let's see, I've already used an X and an H. I guess I'll call this Y, and this angle here is 71. So I'm once again dealing with an opposite and adjacent side. That means the tangent of 71 is equal to Y over 250, right? Opposite over adjacent. And again, you can think of that tan 71 over 1 if you like. Cross multiply, you get 1 times Y, or just Y, equals 250 times the tangent of 71. And at that point, you'll want to go to your calculator and type in 250 times the tangent of 71, and you get Y as approximately 726.0527. So again, I'll stick with the same nearest tenth since they haven't mentioned a new rounding to me, and I'll say the tower is approximately 726.1 meters tall. So there you have it. I hope you found this helpful. If you have any questions, feel free to send me an email. And if you like the video, please comment and subscribe. Have a great day.